Hello viewers, in today's class we are going to discuss one important problem from areas of bounded regions, right? So here we'll discuss one problem related to the application of definite integrals, right? So here we have the problem, find the area of the region bounded by this region, that is the points x comma y, such that which lies on this region, right? So here we have x square plus y square less than or equal to 1, and here less than or equal to x plus y, right? So here we see that we have two regions. The first one, that is R1, is the circle which is given by x square plus y square less than or equal to 1, and R2 is the region which is given by this straight line, right? So this represents a circle. R1 represents a circle, R2 represents a straight line, right? And the region which we have to find out is the common region between this circle and straight line. So we have to find the area of the bounded region R, which is the intersection of these two regions, right? So the region which is common to, or the area which is common to the circle and the straight line, right? So in order to solve this problem or to proceed further, let us first draw a rough sketch of R1 and R2. Now viewers, R1 represents a circle which is x square plus y square is equal to 1, which can also be written as 1 square, right? So this circle is of the standard form, that is x square plus y square is equal to a square, where a is the radius of the circle, which is 1, or unit radius in this case, right? So we have a circle whose origin or whose center is at the origin, right? And the radius is 1. So we can draw a circle. This is the rough diagram, and we have a circle like this, right? So this is the circle whose center lies at the origin and radius is 1. Now the second equation which is given is the equation of a straight line, right? So we have the line x plus y is equal to 1, and we see that if we convert this line into intercept form, we have x over 1 y over 1 is equal to 1. So this line must pass through these 2 points, right? That is this point is 1 comma 0, and this point is 0 comma 1, right? So viewers, we have the line like this, and this is the straight line x plus y is equal to 1, and this is the circle x square plus y square is equal to 1, right? Now the next step, once we have drawn this circle and the line on the coordinate plane, the next step is to identify the region whose area is to be calculated, right? So here see, we have x square plus y square is less than or equal to 1, and we see that from the theory of inequalities, right? We know that this point, that is 0 comma 0, it satisfies this inequality, right? So we have 0 less than or equal to 1, so this point 0 comma 0 satisfies this inequality, right? So it means we have to take the region of the circle which lies towards the origin, right, or the interior. So here we have this region, right? Okay, now let us come to the second inequality, which is x plus y greater than or equal to 1, right? Now here if we test this inequality for this point, that is 0 comma 0, and if we substitute 0 comma 0 in this inequality, we see that we have 0 plus 0 greater than or equal to 1, and this is 0 greater than or equal to 1, and which is obviously false, right? So it implies that this inequality doesn't satisfy this point 0 comma 0, right? So the feasible region is the region which lies above this line, right? So we see that the region which is whose area is to be calculated is this region, right? So we have to find the area of this region. So now viewers, we have thus seen that this shaded region represents our required area, which is R1 intersection R2, right? And we have to find the area of this region using the concept of integration, right? So for this, what we will do, we'll take a strip like this, right? So this is a strip, let us call it as PQRS, right? So this is the strip that is PQRS, and it is known as the vertical strip or the elementary strip, right? And we see that this strip, it runs from this x-axis to the boundary of this circle, right? And between x-axis and the boundary of the circle, it intersects the straight line x plus y is equal to 1, right? So from the theory of definite integrals, we know that the area is given by the integral from a to b and y dx, right, where y is the function that is f of x, and these are the two limits between which we have to find the integral y dx. So now let us express the variable y in terms of x in both these equations, right? So from here we see that y square is equal to 1 minus x square, and y is equal to square root of 1 minus x square, and here we have y is equal to 1 minus x, right? So now viewers, here see, we have to find the area bounded by these two curves, right? So the first curve is the circle and the second curve is the straight line, right? And we see that the circle, it lies above the straight line, right? So if we denote this y by y2 and this y by y1, then we see that area bounded between two curves is given by integral from a to b, and for this y we have y2 minus y1, right? Because if we look at this vertical strip, then it runs from x-axis, the lower end is at x-axis and the upper end is at the circumference of the circle, right? So y2 is greater than y1, because here this end of the vertical strip, it lies on the straight line, right? So we have y2 minus y1 dx, right? and y1 is given by 1 minus x, and y2 is given by square root of 1 minus x square, and a is the lower limit and b is the upper limit, and in this case the limits runs from 0 to 1, right? That is 0 to 1, because the origin has the coordinates 0 comma 0, and the end point here is having the coordinate 1 comma 0. So the limits runs from 0 to 1, and this area, the bounded region, is sliced into infinitely many vertical strips, right? So the lower end lies at the x-axis and the upper end lies on the circle, right? So we have to take y2 minus y1, right? So now if we substitute the values of y2 and y1, we have a square root of 1 minus x square, and here we have 1 minus x, right? And we have here dx. Now we have to calculate this integral. Now let us separately calculate these two integrals. So I1 is from 0 to 1 square root of 1 minus x square, and to calculate this integral we have to make use of the result, that is integral of square root of a square minus x square is given by x over 2 square root of a square minus x square plus a square over 2, and here we have sine inverse x over a, right? So if we compare this form with this one, we see that here 1 can be written as 1 square. So the value of a is equal to 1, right? So now I1 is given by x over 2. So we have x over 2 square root of a square minus x square, which is 1 square minus x square, and a is 1, so 1 square is 1, so this is 1 over 2 sine inverse x over 1, right? And the limits are from 0 to 1. And now if we substitute the limits when we take x equal to 1, so this term is 0, and here we have half sine inverse 1, and when we take 0, then this term is 0, and this term is also 0, because sine inverse 0 is 0. So we have only this term, and sine inverse 1 is pi over 2, so here we have pi over 4, right? Okay, and I2 is given by this integral, that is 0 to 1. We have 1 minus x dx, and the integral of 1 dx is x, and here we have x square over 2, and the limits are from 0 to 1. When we take x is equal to 1, we have 1 minus 1 square over 2, and when we take x equal to 0, we have here 0, so here we have 0, and 1 minus half is half, right? So we have I1 is equal to pi over 4, I2 is half, so therefore the area of this shaded region is now given by I1 minus I2, right? And I1 is pi over 4 and I2 is half, right? So we have the area pi over 4 minus half square units, right? So viewers, this is how we solve this problem.